the dynamic heart of our solar system. At the center of our solar system sits the Sun, a colossal ball of searing plasma, a nuclear reactor that provides the warmth and light essential for life on Earth. But the Sun is far more than just a bright, warm beacon in the sky. It's a dynamic, ever-changing star, driven by complex processes that create dramatic and explosive events, the most powerful of which are solar storms. To truly understand solar storms, we must first understand the anatomy of the Sun itself. The Sun's massive size, nearly 109 times the diameter of Earth, holds sway over the entire solar system with its immense gravity. But it is the Sun's internal structure that gives rise to the solar storms we observe from Earth. The Sun is divided into several layers, each playing a critical role in its behavior and energy production. Deep in the heart of the Sun, the core is where nuclear fusion takes place. Here, temperatures soar to around 15 million degrees Celsius, and pressures are so immense that hydrogen atoms are forced together to form helium. This fusion process releases vast amounts of energy in the form of gamma rays, but the journey for this energy to reach the surface is long and slow. Surrounding the core is the radiative zone, where energy generated in the core is transferred outward through radiation. It takes an astonishingly long time, up to 100,000 years, for this energy to make its way through this layer. This slow process happens because photons, the particles of light, constantly collide with particles of gas in the Sun, being absorbed and re-emitted in random directions. Above the radiative zone, the temperature drops, and the gas here is cooler and denser. In this convective zone, energy is transferred by convection. Hot plasma rises to the surface, cools, and then sinks back down in a continuous loop. This movement creates convection currents that play a significant role in the behavior of the Sun's magnetic field. The surface of the Sun, known as the photosphere, is what we see when we look up at the Sun from Earth. It is from this relatively thin layer, only a few hundred kilometers thick, that the Sun emits light into space. The photosphere is where sunspots, dark patches of magnetic activity, appear. These sunspots are the seeds of solar storms. Above the photosphere lies the chromosphere, a thin layer of hot gas, and beyond it, the Sun's outer atmosphere, the corona. The corona, visible during a total solar eclipse, is where some of the most violent solar storms originate. Temperatures in the corona can exceed 1 million degrees Celsius, far hotter than the surface below. A mystery that still perplexes scientists today. The Sun is not a static object. It operates on a cyclical schedule known as the solar cycle, which spans approximately 11 years. This cycle is marked by fluctuations in solar activity, including the frequency of solar storms, sunspots, and other magnetic phenomena. At the beginning of the solar cycle, the Sun enters a period of minimal activity known as solar minimum, where sunspots are few and solar flares are rare. As the cycle progresses, solar activity increases, reaching a peak known as solar maximum, during which time sunspots cover much of the Sun's surface, and violent solar storms are more frequent. The solar cycle is driven by the Sun's magnetic field, which twists and tangles as the Sun rotates. Over time, the magnetic field becomes more complex, and eventually, it flips entirely. North becomes south, and south becomes north. This magnetic flip occurs around solar maximum and resets the cycle. Scientists closely monitor the solar cycle because it directly influences the likelihood and intensity of solar storms. A period of intense solar activity means a higher probability of powerful eruptions that can have significant effects on Earth. Sunspots are cooler, darker areas on the Sun's surface, where the Sun's magnetic field is particularly strong and concentrated. These magnetic fields inhibit the flow of hot plasma from the Sun's interior, causing the region to cool slightly compared to the surrounding photosphere. Sunspots can vary greatly in size, with some large enough to fit several Earths inside them. While sunspots themselves are relatively calm, they are often the origin points for the most violent solar phenomena. The intense magnetic fields around sunspots can become twisted and stressed over time. When these magnetic fields become too tangled, they can suddenly snap back into alignment, releasing a massive amount of energy in the process. This process is called magnetic reconnection, and it is the cause of solar flares and coronal mass ejections, two types of solar storms that can send bursts of energy and charged particles hurtling through space. The relationship between sunspots and solar storms was first observed in the mid-19th century by English astronomer Richard Carrington. In 1859, Carrington witnessed a solar flare in real time, a bright flash of light from a sunspot. Shortly after, Earth experienced one of the most powerful geomagnetic storms ever recorded, known as the Carrington event, which we will discuss in later chapters. The sun's magnetic field is one of the most critical factors in the formation of solar storms. Magnetic fields on the sun are generated by the movement of plasma within the convective zone, a process known as the solar dynamo. The magnetic field is constantly shifting, twisting, and reconnecting, and these movements can lead to explosive releases of energy. Understanding the sun's magnetic field is key to predicting solar storms. In recent decades, space missions like NASA's Solar Dynamics Observatory and the European Space Agency's Solar and Heliospheric Observatory, SOHO, have provided us with valuable insights into the structure of the sun's magnetic field and how it influences solar activity. These observations help scientists forecast solar storms and their potential impact on Earth. The sun's corona presents some of the most intriguing mysteries in solar physics. Despite being further from the core, the corona is significantly hotter than the photosphere. This temperature paradox, known as the coronal heating problem, is still not fully understood. Scientists believe that magnetic waves, known as Alf-Venn waves, may play a role in heating the corona by transferring energy from the sun's interior. The corona is also where solar storms like coronal mass ejections originate. Understanding the complex dynamics of the corona is crucial for predicting when and where solar storms will occur. With each new discovery, we move closer to unlocking the secrets of this mysterious outer layer. As we look deeper into the sun's behavior and the powerful forces that govern it, we can begin to unravel the mystery of solar storms, the explosive events that occasionally burst from the sun and affect everything in their path, including Earth itself. The sun's fiery activity is a constant reminder of the delicate balance that sustains life in our solar system and the hidden forces that can disrupt it in an instant. Solar flares. The fiery explosions of energy. Solar flares are one of the most dramatic and powerful events that occur on the sun. These sudden bursts of energy release tremendous amounts of light, heat, and charged particles into space, impacting the entire solar system. But what exactly causes a solar flare, and how does it influence our planet? In this chapter, we will explore the inner workings of solar flares, uncover their role in solar storms, and understand how they connect to the intricate dance of the sun's magnetic field. What is a solar flare? A solar flare is a sudden, intense burst of radiation that originates from the sun's atmosphere, specifically from the areas near sunspots. Solar flares occur when the magnetic energy stored in the sun's atmosphere is suddenly released. This can happen when magnetic field lines near sunspots become tangled and twisted. The process by which they snap back into a more relaxed configuration is known as magnetic reconnection. This release of energy generates radiation across the electromagnetic spectrum, from visible light to X-rays and gamma rays. The most powerful solar flares can emit more energy in a few minutes than all the energy released by Earth's entire power consumption over a year. Solar flares are classified into 5 categories based on their intensity, with each class being 10 times more powerful than the last: A, B, C, M, and X. These flares are measured by the strength of the X-rays they emit, particularly in the wavelength range of 1 to 8 angstroms, as detected by satellites like GOES, Geostationary Operational Environmental Satellites. The energy for solar flares comes from the sun's complex magnetic field. The sun is made of plasma, a hot, ionized gas that generates electric currents, which in turn produce magnetic fields. These fields are in constant motion, twisted and stretched by the sun's rotation and the convective movements of plasma. The surface of the sun, where the photosphere and chromosphere reside, is particularly active, with magnetic loops arching out into the sun's outer atmosphere. The corona. Over time, these magnetic loops can become tangled and store immense amounts of energy. When the magnetic field lines snap or reconnect, it releases this energy in the form of a solar flare. This event can happen suddenly, creating a bright flash of radiation that can be observed by space telescopes monitoring the sun. The areas most prone to solar flares are active regions, where the sun's magnetic field is particularly strong and complex. These regions often correspond to sunspots, dark patches on the sun's surface that indicate areas of lower temperature and intense magnetic activity. Solar flares are often accompanied by other solar phenomena, such as coronal mass ejections, CMEs, which we will explore in detail in the following chapters. Together, these explosive events make up the core of solar storms, affecting not only the sun's immediate surroundings, but also the rest of the solar system, including Earth. To understand the scale of solar flares, scientists classify them based on their X-ray intensity. This classification helps predict the potential impact of a flare, particularly on Earth's space weather. A-class flares are the weakest solar flares. They are almost undetectable and have minimal effect on space weather. B-class flares are slightly stronger than A-class flares, but still too weak to have any noticeable impact on Earth. C-class flares are moderate and can cause brief radio blackouts in the polar regions. They are common during the solar cycle, but rarely cause significant disruptions. M-class flares are medium-sized flares that can cause brief radio blackouts and increase radiation levels in Earth's upper atmosphere. M-class flares are strong enough to produce auroras and can be disruptive to communication systems. X-class flares are the most powerful solar flares, with the potential to cause significant disruptions to satellites, GPS systems, and power grids on Earth. X-class flares can also produce intense radiation storms that pose a threat to astronauts and space missions. The strongest flares on record are X-class flares, with the most powerful ever observed being classified as an X-28 flare in 2003. Each class of solar flare is further subdivided based on intensity. For example, an M2 flare is twice as strong as an M1 flare, while an X3 flare is 3 times stronger than an X1 flare. While solar flares occur far from Earth, their effects can be felt across our planet in the form of space weather. Space weather refers to the changing conditions in Earth's magnetosphere, ionosphere, and atmosphere due to solar activity. When a solar flare occurs, it sends a burst of high-energy radiation and charged particles toward Earth. While Earth's atmosphere protects us from the harmful effects of this radiation, solar flares can still impact technology and communications in significant ways. Solar flares, especially X-class and M-class, can cause sudden ionospheric disturbances that result in radio blackouts. These occur when high-energy X-rays from a solar flare ionize the upper layers of Earth's atmosphere, particularly in the D region of the ionosphere. This increase in ionization absorbs radio signals, causing communication disruptions, particularly for aviation and maritime industries that rely on high-frequency, HF, radio communication. Solar flares can produce high levels of radiation, which can affect satellites orbiting Earth. The increased radiation can cause malfunctions in satellite electronics, disrupt data transmission, and degrade solar panels. Space agencies and satellite operators closely monitor solar activity to protect satellites from these effects. Solar flares produce solar energetic particles, SEPs, which are high-energy protons and electrons accelerated by the flare's release of energy. These particles can pose a threat to astronauts aboard spacecraft and at the International Space Station, ISS, as they can penetrate spacecraft shielding and increase radiation exposure. One of the more beautiful effects of solar flares is the increased activity of auroras, the northern and southern lights. Solar flares, along with CMEs, send charged particles into Earth's magnetosphere, where they interact with oxygen and nitrogen in the atmosphere. These interactions produce the stunning light displays we see as auroras. While flares alone are often not enough to create intense auroras, they can enhance auroral activity when combined with a CME. Although solar flares alone do not cause geomagnetic storms, They often precede events like CMEs, which are responsible for major disturbances in Earth's magnetic field. We will delve deeper into geomagnetic storms in later chapters. Throughout recorded history, several solar flares have stood out for their intensity and the effects they had on Earth. One of the most famous examples is the Carrington event of 1859, named after British astronomer Richard Carrington, who witnessed the flare. The Carrington event remains the most powerful solar flare and geomagnetic storm on record. During the Carrington event, telegraph systems around the world failed, with some operators reporting sparks and fires caused by the intense electrical currents induced by the storm. Auroras were seen as far south as the Caribbean, and the night sky was lit up with vibrant displays of light. If an event of this magnitude were to happen today, it could cause widespread damage to global communications, power grids, and satellite systems. More recently, the X-28 flare of 2003 disrupted satellite communications and air traffic control systems. This flare was so powerful that it temporarily blinded satellites designed to monitor solar activity, making it difficult to measure its true intensity. While such massive solar flares are rare, they serve as a reminder of the potential dangers posed by the sun's activity. As we continue to explore space and become more reliant on satellite technology, understanding and predicting solar flares becomes ever more important. The energy released in a single solar flare is awe-inspiring. It is a reminder of the sun's incredible power and its ability to shape the environment of our solar system. But solar flares are only part of the story. In the vast corona, the sun's outer atmosphere, even more powerful events take place. Coronal mass ejections, CMEs, the massive explosions of plasma that hurl billions of tons of solar material into space. These are the true titans of solar storms. Coronal mass ejections, the giants of solar storms. While solar flares are impressive bursts of radiation, the real heavyweights of solar storms are coronal mass ejections, CMEs. These colossal eruptions of solar material can have far-reaching effects throughout the solar system, and when they collide with Earth's magnetic field, they can unleash geomagnetic storms with the potential to disrupt technology, satellites, and even power grids. In this chapter, we will dive into the nature of coronal mass ejections, exploring their formation, impact, and the ways in which they shape space weather. CMEs represent the sun at its most violent, ejecting billions of tons of plasma and magnetic fields into the solar system with immense force. What is a coronal mass ejection? A coronal mass ejection is a large-scale eruption of plasma and magnetic field lines from the sun's outer atmosphere, the corona. While solar flares release electromagnetic radiation, CMEs expel massive quantities of charged particles, including protons, electrons, and heavier ions, at speeds ranging from hundreds to thousands of kilometers per second. A CME can eject over 1 billion tons of solar material into space, enough to fill several Earth-sized objects. CMEs often occur in conjunction with solar flares, but they are distinct phenomena. A solar flare releases a burst of light and energy, while a CME launches huge clouds of solar plasma into space. When these clouds of plasma reach Earth, they can interact with our planet's magnetic field, potentially causing geomagnetic storms and auroras. Unlike solar flares, which take only 8 minutes for their light and radiation to reach Earth, CMEs can take 1 to 4 days to arrive, depending on their speed. This delay gives scientists a crucial window of time to predict their impact on Earth and prepare for any potential disruptions. How do CMEs form? The formation of a CME is closely tied to the sun's magnetic field. The sun's magnetic field lines are constantly shifting, twisting, and stretching due to the movement of plasma within the sun's convective zone. This creates regions of intense magnetic stress in the corona, particularly around sunspots. When the magnetic field lines become too twisted, they can reconnect violently, releasing massive amounts of energy and ejecting plasma from the corona into space. This process, known as magnetic reconnection, is responsible for both solar flares and CMEs. However, while solar flares release radiation, CMEs eject actual solar material. CMEs are more likely to occur during periods of high solar activity, such as solar maximum, when sunspots and magnetic activity are at their peak. These periods of intense activity are part of the 11-year solar cycle, during which the sun's magnetic poles flip, creating a buildup of magnetic stress that eventually leads to more frequent CMEs and solar flares. A typical CME consists of several key components. This is the outermost part of the CME and contains dense, fast-moving plasma. As it moves through space, the leading edge of a CME pushes against the solar wind, creating a shockwave similar to a sonic boom. This shockwave can accelerate particles to near-relativistic speeds, producing solar energetic particles, SEPs, which pose a threat to astronauts and spacecraft. At the center of the CME is a large, twisted magnetic structure filled with solar plasma. This core contains the bulk of the mass ejected during the CME. The magnetic field lines in the core can interact with Earth's magnetic field if the CME is Earth-directed, potentially causing geomagnetic storms. CMEs travel through the solar wind, a continuous stream of charged particles flowing from the sun. When a CME moves through the solar wind, it can accelerate particles, creating disturbances that affect the entire heliosphere, the bubble of space dominated by the sun's magnetic influence. The shape and size of a CME can vary dramatically. Some CMEs are small and relatively harmless, while others can be massive, spanning millions of kilometers across. The most powerful CMEs directed toward Earth are capable of triggering major space weather events that can disrupt technology and power infrastructure on our planet. When a CME is directed toward Earth, it has the potential to cause significant disruptions in what we call space weather. While Earth's magnetic field offers protection from the charged particles of the solar wind, a CME's intense magnetic field and plasma can overwhelm our planet's defenses, triggering a geomagnetic storm. Geomagnetic storms occur when the CME's magnetic field interacts with Earth's magnetosphere, the region of space dominated by Earth's magnetic field. If the CME's magnetic field is aligned in the opposite direction of Earth's magnetic field, a phenomenon known as southward magnetic orientation, it can connect with our magnetic field, transferring energy and charged particles into the magnetosphere. CMEs can have a range of effects on Earth, depending on their size, speed, and magnetic orientation. The most significant impacts include: when a CME interacts with Earth's magnetosphere, it can trigger geomagnetic storms, which can last for hours or even days. During a geomagnetic storm, the magnetic field lines of Earth's magnetosphere become distorted, and charged particles are funneled into Earth's upper atmosphere. This can lead to disruptions in satellite communications, GPS signals, and power grids. One of the most significant geomagnetic storms in recent history occurred in 1989, when a powerful CME caused the collapse of the Hydro-Quebec power grid in Canada, leaving 6 million people without electricity for several hours. One of the more beautiful effects of a geomagnetic storm is the enhancement of auroras, the northern and southern lights. Auroras are caused by the interaction of charged particles with Earth's atmosphere, particularly with oxygen and nitrogen molecules. During a geomagnetic storm, these interactions are intensified, creating spectacular displays of light that can be seen much farther from the poles than usual. Some of the most intense storms have produced auroras visible as far south as the equator. CMEs can pose a serious threat to satellites in orbit. The charged particles from a CME can damage satellite electronics, degrade solar panels, and interfere with data transmission. Satellites in geostationary orbits are particularly vulnerable as they remain in the same position relative to Earth and are directly exposed to space weather. One of the most dangerous effects of a CME is its impact on Earth's power grids. The interaction between a CME and Earth's magnetic field can induce electric currents in the ground, known as geomagnetically induced currents, GICs. These currents can overload power transformers and cause widespread blackouts, as happened during the 1989 Hydro-Quebec blackout. Modern power grids are highly interconnected, making them more vulnerable to the cascading effects of a major geomagnetic storm. Astronauts in space are particularly vulnerable to the effects of CMEs. The charged particles from a CME can penetrate spacecraft shielding, increasing radiation exposure and posing a significant health risk. For this reason, space agencies closely monitor solar activity and may delay spacewalks or other critical missions when a CME is expected. The most famous and powerful geomagnetic storm ever recorded was the Carrington event of 1859. Named after the British astronomer Richard Carrington, who observed the associated solar flare, the Carrington event was caused by a massive CME that struck Earth with incredible force. Telegraph systems around the world failed, with some telegraph operators reporting sparks and even fires caused by the induced electric currents. Auroras were seen as far south as the Caribbean, lighting up the night sky with brilliant displays of color. If a similar event were to occur today, the consequences could be far more severe, given our reliance on satellite technology and electricity. Scientists estimate that the Carrington event was roughly an X-45 class flare, far more powerful than anything we've seen in recent decades. Such an event would have the potential to disrupt global communications, damage satellites, and cause widespread power outages. Predicting when and where a CME will occur is a challenging task, but space weather forecasters have made significant advancements in recent decades. Instruments like NASA's Solar Dynamics Observatory, SDO, and the European Space Agency's Solar and Heliospheric Observatory, SOHO, monitor the sun continuously, tracking sunspot activity, solar flares, and emerging CMEs. When a CME is detected, scientists can estimate its speed and direction using data from spacecraft positioned between Earth and the Sun, such as NASA's Advanced Composition Explorer, AC. This gives us valuable time to prepare for the impact, whether by protecting satellites, adjusting power grid operations, or warning astronauts. Though we cannot prevent CMEs, understanding their behavior and preparing for their effects is crucial as our reliance on technology grows. These titanic eruptions from the Sun remind us of the incredible forces at play in our solar system, forces that, while distant, have the power to shape life on Earth in profound ways. The sheer scale of a coronal mass ejection is mind-boggling. With billions of tons of solar material flying through space at incredible speeds, CMEs are the ultimate example of the Sun's explosive power. But these eruptions are not the only influence the Sun has on our planet. There is a continuous flow of charged particles streaming from the Sun, shaping our space environment in subtler but equally important ways. The solar wind, the continuous breath of the Sun. Beyond the explosive eruptions of solar flares and coronal mass ejections, the Sun has a more constant but equally powerful influence on the space around it. The solar wind. This continuous flow of charged particles streams from the Sun's outer layers, shaping the space environment throughout the solar system and interacting with the magnetic fields of planets, including Earth. While less dramatic than solar storms, the solar wind is a key component of space weather and plays a crucial role in everything from auroras to planetary magnetospheres. In this chapter, we will explore the nature of the solar wind, how it is generated, and the profound impact it has on the solar system. The solar wind may seem like a gentle breeze compared to the titanic forces of CMEs, but its effects are far-reaching and constant, shaping the very space we live in. What is the solar wind? The solar wind is a stream of charged particles, mostly electrons, protons, and alpha particles, helium nuclei, that flows outward from the Sun's corona, the outermost part of the Sun's atmosphere. The solar wind is composed of plasma, an electrically charged state of matter where the electrons and protons are no longer bound together in atoms. This plasma flows continuously in all directions, carrying the Sun's magnetic field with it and creating the heliosphere, a vast bubble of space dominated by the Sun's influence. The solar wind is not uniform. Its speed and density vary depending on where it originates on the Sun. It is typically divided into two components. Originating from coronal holes, regions in the Sun's corona where the magnetic field lines are open and allow plasma to escape easily, the fast solar wind moves at speeds of around 700 kilometers per second. Emanating from areas where the magnetic field lines are more complex and twisted, such as near the Sun's equator, the slow solar wind travels at roughly 400 kilometers per second. The slow solar wind is more variable and turbulent than its faster counterpart. While solar flares and CMEs are short-lived, violent events, the solar wind is a continuous outflow of material from the sun, creating a sort of cosmic breeze that flows through the entire solar system. It extends far beyond the orbit of Pluto, defining the outer edges of the solar system, where the solar wind meets the interstellar medium, the space between stars. The solar wind originates from the sun's corona, where temperatures exceed 1 million degrees Celsius. This high temperature is key to understanding the solar wind's creation. The particles in the corona are so energetic that they can escape the sun's gravitational pull, streaming out into space at high speeds. The corona is a dynamic and mysterious region of the sun, constantly shifting and evolving due to the complex interplay of magnetic fields and plasma. It's also much hotter than the sun's surface, the photosphere, which is only about 5,500 degrees Celsius. This is known as the coronal heating problem, and scientists are still trying to fully understand why the corona is so much hotter than the layers below it. One theory is that waves of energy, known as Alf-Venn waves, are generated in the convective zone and heat the corona as they propagate outward. As the corona's superheated plasma escapes into space, it carries with it part of the sun's magnetic field, forming what is known as the interplanetary magnetic field, IMF. This magnetic field twists and spirals as the sun rotates, creating the so-called Parker spiral, named after the astrophysicist Eugene Parker, who first predicted the existence of the solar wind in the 1950s. The Parker spiral helps explain why the solar wind's magnetic field is not straight, but rather curves outward, shaping the space weather around planets like Earth. The solar wind has a constant and profound effect on Earth's magnetosphere, the magnetic bubble that surrounds our planet and protects us from much of the sun's harmful radiation. Earth's magnetic field acts as a shield, deflecting most of the solar wind particles around the planet. However, the solar wind can still interact with the magnetosphere, particularly at the poles, where Earth's magnetic field lines dip into the atmosphere. One of the most beautiful and visible effects of the solar wind is the creation of auroras, also known as the northern and southern lights. When charged particles from the solar wind enter Earth's magnetosphere, they are funneled toward the poles, where they collide with oxygen and nitrogen atoms in the atmosphere. These collisions excite the atoms, causing them to release energy in the form of light, producing the stunning displays of green, red, and purple light that we see as auroras. The intensity and frequency of auroras are closely tied to the strength of the solar wind. During periods of high solar activity, such as solar maximum, the solar wind becomes more turbulent, and auroras can be seen at lower latitudes than usual. In extreme cases, auroras have been observed as far south as the Caribbean. While the solar wind is generally a constant and relatively mild flow of particles, it can occasionally cause geomagnetic storms when it interacts with Earth's magnetosphere. These storms are more likely during periods of increased solar activity, such as when a CME accompanies the solar wind. Geomagnetic storms can disrupt satellite communications, GPS systems, and even power grids, as we've discussed in previous chapters. The solar wind plays a significant role in space weather, the conditions in space that affect Earth's technological systems. Satellite orbits, spacecraft electronics, and radio communications can all be impacted by fluctuations in the solar wind. For example, satellites in low Earth orbit experience drag due to the expansion of Earth's upper atmosphere when it absorbs energy from the solar wind. This can cause satellites to lose altitude over time, requiring adjustments to keep them in proper orbit. Additionally, the solar wind's interaction with Earth's magnetic field can induce currents in power lines and pipelines, potentially damaging infrastructure during strong solar storms. Space weather forecasters constantly monitor the solar wind to predict these events and mitigate their effects. The solar wind's influence extends far beyond Earth. It affects every planet in the solar system, as well as moons, comets, and even spacecraft traveling through interplanetary space. Planets with magnetic fields, such as Jupiter, Saturn, and Mercury, have their own magnetospheres, which interact with the solar wind in much the same way Earth's does. These interactions can create auroras on other planets. For example, Jupiter's auroras are far more powerful than Earth's due to its stronger magnetic field and the influence of its volcanic moon, Io, which provides additional charged particles. Mars, unlike Earth, does not have a global magnetic field to protect it from the solar wind. Instead, Mars has small, localized magnetic fields that provide limited protection. Over billions of years, the solar wind has gradually stripped away much of Mars's atmosphere, contributing to the planet's transformation from a warm, wet world into the cold, dry desert we see today. NASA's MAVEN, Mars Atmosphere and Volatile Evolution, mission has been studying how the solar wind continues to erode Mars's atmosphere. The findings suggest that Mars's atmospheric loss accelerated during periods of high solar activity, particularly during solar maximum, when the solar wind becomes more intense. The solar wind extends far beyond the orbits of the planets, creating the heliosphere, a vast bubble of solar plasma that shields the solar system from the interstellar medium. At the edge of the heliosphere lies the heliopause, the boundary where the solar wind's pressure balances with the pressure of the interstellar medium. NASA's Voyager 1 spacecraft crossed the heliopause in 2012, becoming the first human-made object to enter interstellar space. Voyager 2 followed suit in 2018. These spacecraft have provided invaluable data about the solar wind's influence at the farthest reaches of the solar system. While we have made significant progress in understanding the solar wind, there is still much to learn about its behavior and impact on the solar system. Missions like NASA's Parker Solar Probe, launched in 2018, are designed to study the solar wind up close by, flying directly through the sun's corona. The Parker Solar Probe will help scientists answer fundamental questions about how the solar wind is accelerated and why the corona is so much hotter than the sun's surface. Additionally, the European Space Agency's Solar Orbiter is providing new insights into the sun's poles, regions that are difficult to observe from Earth. These missions are part of an ongoing effort to understand the sun's behavior and predict its impact on Earth and other planets. The solar wind may seem gentle compared to the violent eruptions of solar flares and CMEs, but its influence is profound. It shapes the space environment, drives space weather, and extends the sun's reach far beyond its surface. As we continue to explore the solar system, understanding the solar wind will be crucial for protecting astronauts, spacecraft, and the technology we depend on. The constant flow of solar wind through the solar system connects all planets in a delicate balance with the sun. But while this solar breeze is a constant presence, it's the dramatic, episodic events, solar flares and CMEs, that truly shake the solar system. And when they align with Earth's path, we are reminded of the immense power of the star that sustains us. The Sun-Earth Connection. How solar storms affect our planet. Solar storms, those intense outbursts of energy from the sun, have a profound impact on Earth. While we are well protected by our planet's atmosphere and magnetic field, solar activity can disrupt our technology, communications, and even our power grids. But beyond the potential for disruption, solar storms also create beautiful natural displays, such as the auroras, reminding us of the intricate connection between our sun and our planet. In this chapter, we will explore how solar storms influence Earth, from the upper atmosphere to the technologies we rely on daily. By understanding these interactions, we gain insight into the delicate balance between the sun's power and our ability to harness and protect against it. One of Earth's greatest defenses against the sun's constant bombardment of charged particles is its magnetosphere. The magnetosphere is a vast protective bubble of magnetic field generated by the movement of molten iron and nickel in Earth's outer core. It extends tens of thousands of kilometers into space and deflects most of the harmful solar wind and cosmic radiation away from the planet. The magnetosphere works by guiding charged particles along its field lines, directing them toward the poles and preventing them from reaching the Earth's surface. Without this protective magnetic shield, life on Earth would be exposed to far more intense radiation from the sun, making our planet far less hospitable. However, when solar storms like coronal mass ejections, CMEs, or strong solar flares occur, the magnetosphere can be temporarily overwhelmed. These interactions can lead to geomagnetic storms, disruptions in technology, and brilliant displays of auroras. Geomagnetic storms occur when solar storms interact with Earth's magnetosphere, causing temporary but intense disturbances. These storms are most commonly triggered by CMEs that strike Earth's magnetic field, transferring energy and charged particles into the magnetosphere. A geomagnetic storm typically unfolds in 3 phases. When a CME or high-speed solar wind stream reaches Earth, it compresses the magnetosphere, causing a sudden increase in the magnetic field strength. This is known as the storm's sudden commencement. In the main phase, the CME's magnetic field interacts with Earth's magnetosphere. If the magnetic field of the CME is oriented southward, it can more easily connect with Earth's northward magnetic field lines, allowing charged particles and energy to enter the magnetosphere. This leads to the most intense part of the geomagnetic storm. As the CME passes and the magnetosphere begins to stabilize, Earth's magnetic field gradually returns to its normal state over a period of hours to days. Geomagnetic storms can range in intensity from mild disturbances, which have little effect, to major storms that can disrupt satellite operations, GPS systems, and power grids. One of the key factors that determine the severity of a geomagnetic storm is the alignment of the CME's magnetic field with Earth's. If the fields are aligned oppositely, the impact is far more significant. One of the most vulnerable systems to solar activity is Earth's fleet of satellites. Satellites orbit in space, outside the protective layers of Earth's atmosphere, making them particularly susceptible to solar radiation and charged particles. The radiation from solar flares and the influx of charged particles during a CME can damage the delicate electronics aboard satellites. This is particularly problematic for satellites in geosynchronous orbit, which remain in a fixed position relative to Earth. Solar storms can cause single-event upsets, where charged particles interfere with satellite processors, leading to temporary malfunctions or permanent damage to critical components. Solar storms can also cause radio frequency interference, disrupting data transmission between satellites and ground stations. This can impact weather forecasting, satellite TV and radio services, and even military communications. Global Positioning System, GPS satellites, are particularly vulnerable to the effects of solar storms. Geomagnetic storms can disrupt the signals that GPS satellites send to receivers on Earth, leading to inaccurate positioning data. This can be problematic for industries that rely on precise navigation, such as aviation, maritime shipping, and autonomous vehicles. The energy from solar storms can cause Earth's upper atmosphere to expand, increasing the density of the thermosphere. This increased atmospheric density creates more drag on satellites in low Earth orbit, causing them to lose altitude over time. Satellites must use onboard thrusters to counteract this drag, which shortens their operational lifetimes. While satellite damage is a significant concern, perhaps the greatest threat from solar storms comes in the form of power grid failures. During a geomagnetic storm, the influx of charged particles can induce geomagnetically induced currents, GICs, in power lines and transformers. These currents can overload electrical systems, leading to widespread blackouts. One of the most famous examples of this occurred in 1989 during the Hydro-Quebec blackout. A powerful CME struck Earth, inducing strong currents in the power grid in Quebec, Canada. Within 90 seconds, the power grid collapsed, leaving 6 million people without electricity for several hours. The blackout caused significant economic losses and highlighted the vulnerability of modern power grids to space weather events. Since then, power companies have taken steps to mitigate the effects of solar storms. Many utilities now monitor solar activity and geomagnetic conditions in real time, allowing them to take protective measures, such as shutting down vulnerable transformers or redistributing electrical loads during severe storms. However, the risk of another major geomagnetic storm, like the Carrington event of 1859, remains a concern for the global power grid. Another group at risk during solar storms is astronauts and space missions. Solar energetic particles, SEPs, from solar flares and CMEs can penetrate spacecraft shielding, increasing radiation exposure for astronauts. This is particularly dangerous during spacewalks or missions beyond low Earth orbit, such as those planned for the Moon or Mars. Space agencies like NASA closely monitor solar activity to protect astronauts from radiation hazards. If a major solar storm is detected, astronauts aboard the International Space Station, ISS, are instructed to take shelter in more heavily shielded areas of the station, such as the Russian-built Zvezda module. Future missions to deep space will require even more advanced shielding and radiation protection to ensure the safety of astronauts during solar storms. While solar storms can cause significant disruption, they also produce one of nature's most awe-inspiring displays: auroras. Also known as the northern and southern lights, auroras are the result of charged particles from the solar wind and CMEs interacting with Earth's atmosphere. When these particles enter Earth's magnetosphere, they are funneled toward the poles, where they collide with oxygen and nitrogen atoms in the atmosphere. These collisions excite the atoms, causing them to emit light. The color of the aurora depends on the type of atom involved. Oxygen produces green and red auroras, while nitrogen creates blue and purple hues. Auroras are most commonly seen near the poles, but during strong geomagnetic storms, they can be visible at much lower latitudes. For example, during the Carrington event, auroras were seen as far south as the Caribbean. These natural light displays are not only beautiful, but also serve as a visible reminder of the powerful forces at work in the Sun-Earth system. While solar storms can have dramatic effects on Earth's technology, their influence on climate is less direct. The energy released during a solar storm is minuscule compared to the total energy Earth receives from the Sun over time. However, changes in the Sun's activity over long periods, such as during the Maunder Minimum, a period of low solar activity in the late 17th century, have been linked to slight cooling of Earth's climate. The Maunder Minimum coincided with the Little Ice Age, a period of cooler than average global temperatures. While solar activity is just one factor influencing Earth's climate, it is clear that the Sun plays a role in shaping the environment we live in, both on short and long timescales. As our society becomes more dependent on technology, understanding and predicting space weather has become increasingly important. Space weather forecasting relies on a combination of solar observations, satellite data, and computer models to predict when solar storms will occur and how they will impact Earth. Space agencies like NASA, the European Space Agency, ESA, and the National Oceanic and Atmospheric Administration, NOAA, play a crucial role in monitoring solar activity and issuing warnings about potential space weather events. Instruments like the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, provide real-time data on sunspots, solar flares, and CMEs, helping scientists predict when a solar storm is likely to strike Earth. The Sun-Earth connection is a complex and dynamic relationship. While the Sun provides the light and warmth essential for life, its storms can disrupt the technology that modern civilization depends on. By studying solar activity and improving our space weather forecasting abilities, we can better protect ourselves from the potential dangers posed by the Sun's explosive energy. Earth's magnetosphere may shield us from the worst effects of solar storms, but what lies beyond our planet's magnetic cocoon? In the vast reaches of space, the solar wind, solar flares, and CMEs create a challenging environment for spacecraft, astronauts, and future explorers venturing beyond Earth's protective bubble. Solar storms in deep space. Challenges for space exploration. As humanity ventures further into space, beyond Earth's protective magnetosphere, the risks posed by solar storms become even more pronounced. Solar energetic particles, SEPs, cosmic rays, and the constant solar wind present significant challenges for spacecraft, astronauts, and future missions to the Moon, Mars, and beyond. Understanding and preparing for these hazards is essential for the success of long-term space exploration. In this chapter, we will explore the dangers of solar storms in deep space, the technologies and strategies needed to protect space missions, and how future exploration plans, such as the Artemis program and Mars colonization, we'll need to account for the sun's powerful influence. One of the most significant threats to astronauts and spacecraft in deep space is solar radiation. Earth's atmosphere and magnetosphere provide robust protection against solar and cosmic radiation. But once a spacecraft leaves this protective bubble, it is exposed to the full force of space weather. The primary sources of radiation in space are: these high-energy particles are ejected from the sun during solar flares and coronal mass ejections, CMEs. SEPs are composed mainly of protons, electrons, and heavier ions that are accelerated to near-relativistic speeds by the sun's magnetic fields. When a CME or solar flare occurs, SEPs can reach a spacecraft or astronaut in deep space within hours. Unlike SEPs, which originate from the sun, galactic cosmic rays are high-energy particles that come from outside the solar system, likely from supernova explosions and other energetic astrophysical events. GCRs are more constant than SEPs, but present a significant long-term radiation hazard for space travelers, as they can penetrate deep into spacecraft materials and biological tissues. Both SEPs and GCRs pose serious risks to astronauts. Exposure to high levels of radiation can increase the risk of cancer, damage tissues and DNA, and even cause acute radiation sickness. In addition to health risks, radiation can damage spacecraft electronics, degrade solar panels, and disrupt communication systems. Protecting astronauts and spacecraft from radiation is one of the key challenges of deep space exploration. Unlike Earth's atmosphere, which absorbs harmful radiation, spacecraft materials must be designed to block or minimize radiation exposure. However, no material can completely shield against high-energy particles like cosmic rays. Therefore, a combination of strategies is needed to protect space missions from solar storms and cosmic radiation. The most straightforward method of protection is shielding the spacecraft. Modern spacecraft are built with materials that provide some degree of protection from SEPs and GCRs, such as aluminum or polyethylene. Polyethylene is particularly effective because it contains a high percentage of hydrogen, which is better at absorbing high-energy particles than heavier elements like aluminum. For long-duration missions, such as a journey to Mars, future spacecraft may incorporate water or even regolith, lunar or Martian soil, into their designs as additional shielding. Water is an excellent absorber of radiation and can be stored around living quarters to provide a protective barrier for astronauts. In the event of a solar storm, astronauts will need to seek shelter in heavily shielded areas of the spacecraft. Space agencies have designed storm shelters, which are small, reinforced areas where astronauts can take refuge during solar energetic particle events. These shelters are equipped with thicker walls or additional layers of shielding material to minimize radiation exposure during a solar storm. The Orion spacecraft, which NASA plans to use for future deep space missions, is equipped with such a shelter, allowing astronauts to avoid exposure to the worst effects of solar radiation during a solar storm. Space weather forecasting is crucial for protecting astronauts and spacecraft from solar storms. Space agencies monitor the sun continuously using a variety of spacecraft, such as NASA's Solar Dynamics Observatory, SDO, and the SOHO, Solar and Heliospheric Observatory. These missions track sunspots, solar flares, and CMEs, providing early warnings of incoming solar storms. Forecasting solar storms gives astronauts the time to take precautions, such as moving to a storm shelter or delaying spacewalks. However, predicting exactly when and where a CME or solar flare will occur remains a challenge. So spacecraft must be equipped with onboard radiation sensors to alert astronauts to sudden spikes in radiation. NASA's Artemis program, which aims to return humans to the moon and establish a sustainable lunar presence, is a key stepping stone in humanity's journey to Mars and beyond. However, operating on the moon's surface presents unique challenges regarding solar radiation, as the moon lacks both an atmosphere and a global magnetic field to protect against solar storms. Future lunar bases will need to incorporate radiation protection into their designs. One proposed solution is to build habitats underground or use regolith as a natural shield. Regolith is rich in hydrogen and other elements that can absorb solar radiation. By burying habitats beneath the lunar surface or covering them with several meters of regolith, astronauts can reduce their exposure to harmful solar energetic particles. In addition to radiation-shielded habitats, future lunar explorers will need storm shelters for short-term protection during solar storms. These shelters would allow astronauts to quickly take refuge from a solar energetic particle event. The ability to detect and respond to solar storms will be critical for the success of long-duration lunar missions. Mars presents even greater challenges in terms of radiation protection. While the planet has a thin atmosphere, it offers little protection from cosmic radiation and solar energetic particles. Mars also lacks a global magnetic field, leaving the surface exposed to space weather. Astronauts on Mars will be exposed to much higher levels of radiation than on Earth or even on the Moon. The surface of Mars receives a constant bombardment of galactic cosmic rays, and during a solar storm, radiation levels could increase dramatically. NASA's Curiosity rover and Mars Odyssey spacecraft have been studying the radiation environment on Mars, providing valuable data for future human missions. One of the most promising solutions for long-term habitation on Mars is to build habitats underground or within natural formations, such as lava tubes. These structures would provide natural shielding from radiation, offering a safe haven for astronauts during periods of intense solar activity. The journey to Mars, which would take several months, is another critical period when astronauts would be vulnerable to solar storms. Spacecraft traveling to Mars will need to be equipped with radiation shelters and advanced shielding to protect the crew from SEPs and cosmic rays. Solar storm forecasting and onboard radiation monitoring will also be essential for detecting and responding to space weather events during the transit. As we look toward the future of space colonization, the Sun's influence will be a constant factor in planning and design. Whether establishing permanent outposts on the Moon or building colonies on Mars, protecting astronauts and equipment from solar storms will be a priority. Future colonies on the Moon and Mars will need to be designed with radiation protection in mind. Habitats must be built with materials that can withstand high levels of solar radiation, and underground structures may become the norm for long-term habitation. The use of local resources, such as lunar regolith or Martian soil, will be critical for building protective barriers against space weather. Solar power will play a crucial role in sustaining future space colonies. The vast solar energy available in space is a valuable resource, but solar storms can temporarily disrupt power generation by damaging solar panels or reducing their efficiency. Engineers will need to design resilient power systems that can withstand space weather and continue providing energy during solar storms. As space exploration expands, the idea of mining asteroids or the Moon for valuable resources has gained traction. However, industrial activities in space will also be affected by solar storms. Mining equipment, robotics, and transportation systems must be designed to operate in the harsh environment of space, where solar energetic particles can damage electronics and reduce the lifespan of machinery. As we continue to push the boundaries of space exploration, advancing our understanding of solar storms will be key to protecting future missions. Several new technologies and missions are being developed to study solar activity and improve our ability to forecast space weather. Launched in 2018, NASA's Parker Solar Probe is the closest any spacecraft has ever come to the Sun. By flying through the Sun's corona, the Parker Solar Probe is gathering unprecedented data on the behavior of the solar wind, magnetic fields, and solar energetic particles. This data will help scientists better understand how solar storms form and how to predict their impact on space missions. The European Space Agency's Solar Orbiter, launched in 2020, is studying the Sun from a unique vantage point, allowing scientists to observe the Sun's poles for the first time. Understanding the Sun's polar regions is critical for modeling the solar cycle and improving our ability to predict solar storms. Scientists are developing more sophisticated computer models to simulate the Sun's magnetic field and the propagation of CMEs through the solar system. These models will provide more accurate predictions of when and where a solar storm will strike, giving astronauts and space agencies more time to prepare. The future of space exploration is bright, but the challenges posed by solar storms and space weather cannot be underestimated. As humanity pushes further into the cosmos, the Sun will remain a powerful force, shaping the environment in which we explore, live, and thrive. The dangers of solar storms in deep space remind us that while the sun gives life, it also presents challenges that we must overcome to explore the universe. But what happens when these storms reach Earth? The delicate balance between the sun's power and our ability to manage its effects continues as we look closer at the history of Earth's encounters with solar superstorms. The history of solar superstorms. Earth's encounters with the sun's fury. Throughout history, Earth has been struck by powerful solar storms, some of which have left an indelible mark on society, technology, and our understanding of the sun. While we often think of solar storms as distant cosmic events, they have played a critical role in shaping Earth's space environment and have even disrupted human civilization in significant ways. In this chapter, we will explore some of the most significant solar superstorms that have impacted Earth. From the infamous Carrington event of the 19th century to more recent space weather phenomena, these events serve as reminders of the sun's immense power and its capacity to disrupt modern technology and infrastructure. The most powerful geomagnetic storm ever recorded occurred in September of 1859, an event that would later become known as the Carrington event. Named after British astronomer Richard Carrington, who witnessed the associated solar flare, this storm was caused by a massive coronal mass ejection, CME, that struck Earth's magnetosphere with unprecedented force. On the morning of September 1st, Carrington was observing the sun through his telescope, projecting the image onto a screen. As he sketched the sunspots, he saw a sudden bright flash of white light, a solar flare, the largest ever recorded up to that point. Within 48 hours, the CME that followed the flare reached Earth, triggering a geomagnetic storm of incredible intensity. The most immediate impact of the Carrington event was felt in the telegraph system, which was the backbone of communication during the 19th century. Telegraph networks across Europe and North America were disrupted, with many operators reporting sparks flying from their equipment. Some telegraph lines even caught fire, and operators in some regions could continue sending messages despite disconnecting their power supplies, as the geomagnetically induced currents provided enough electricity to keep the systems running. The geomagnetic storm produced auroras that were visible far beyond their usual range. People as far south as Cuba and Hawaii witnessed the northern lights, while in some parts of the world, the auroras were so bright that people reportedly could read newspapers at night by their light. While the Carrington event occurred before the advent of modern electronics and satellite technology, its impact on the telegraph system was a stark warning of the potential damage a similar storm could cause today. Modern estimates suggest that if a Carrington-level event were to strike Earth today, it could cause widespread blackouts, disrupt global communications, and damage satellites, costing the global economy billions of dollars. Another significant solar storm struck Earth in March of 1989, causing one of the most dramatic power grid failures in history. This storm, though less powerful than the Carrington event, serves as a modern example of the destructive potential of space weather. In the days leading up to the event, astronomers observed a series of solar flares and CMEs originating from an unusually large sunspot group. On March 9th, a powerful CME struck Earth's magnetosphere, triggering a geomagnetic storm. The storm reached its peak on March 13th, when it caused a major blackout in Quebec, Canada. The geomagnetic storm induced strong electrical currents in the ground, which flowed into Quebec's power grid. The excessive currents overloaded transformers, causing a sudden failure of the Hydro-Quebec power grid. Within 90 seconds, the entire province of Quebec was plunged into darkness. 6 million people were left without power for 9 hours, and the economic losses from the blackout were estimated to be in the hundreds of millions of dollars. The storm also affected satellites in orbit, causing malfunctions and temporarily knocking out communication systems. NASA's TDRS-1 satellite suffered a significant malfunction, and other satellites experienced increased drag due to the expansion of Earth's atmosphere caused by the influx of solar energy. The 1989 storm highlighted the vulnerability of modern power grids to geomagnetic storms. It also spurred efforts to improve space weather forecasting and to implement safeguards in power grids to prevent future blackouts caused by solar activity. In late October and early November of 2003, a series of powerful solar storms struck Earth, earning the nickname the Halloween solar storms. These storms were among the most intense in modern times and caused widespread disruptions to satellite communications, power grids, and air travel. The Halloween storms began with a massive X-17 class solar flare on October 28th, one of the largest flares ever recorded. This flare was followed by a CME that reached Earth in less than 24 hours, triggering a severe geomagnetic storm. In the days that followed, several more powerful flares and CMEs were observed, including an X-28 class flare on November 4th, the most powerful solar flare ever recorded. While the Halloween storms did not cause widespread blackouts like the 1989 event, they did cause power grid disruptions in parts of Sweden and South Africa. In South Africa, transformers were damaged by geomagnetically induced currents, leading to significant repair costs. The Halloween storms caused major disruptions to satellite operations. The Japanese ADEOS-2 satellite was permanently damaged, and several other satellites experienced malfunctions. GPS signals were severely affected, particularly in high-latitude regions, where solar radiation storms caused signal degradation. Airlines were forced to reroute polar flights to avoid the increased radiation levels. The solar radiation storm associated with the Halloween storms posed a significant risk to astronauts aboard the International Space Station, ISS. Fortunately, the crew was able to take shelter in the more heavily shielded parts of the ISS, but the event highlighted the dangers solar storms pose to human spaceflight. The Halloween solar storms of 2003 underscored the need for improved space weather forecasting and better protection for satellites and power grids. Despite the disruptions, the storms also provided scientists with valuable data on how solar activity impacts Earth's magnetic field and atmosphere. One of the most alarming solar storm events in recent history wasn't one that struck Earth, but one that narrowly missed. In July of 2012, a powerful CME was ejected from the Sun and passed through Earth's orbit. Had this CME occurred just a week earlier, it would have struck Earth directly, potentially causing a geomagnetic storm on par with the Carrington event. NASA's Solar Terrestrial Relations Observatory, STEREO spacecraft, was in the perfect position to observe the CME as it passed by. The data collected from STEREO indicated that the CME was moving at speeds of over 2,000 kilometers per second, fast enough to reach Earth in just 18 hours. The CME was accompanied by a powerful solar radiation storm, which could have caused widespread damage to satellites, power grids, and communication systems if it had been Earth-directed. What if it had hit? Scientists estimate that if the 2012 storm had hit Earth, it could have caused a global economic disaster, with damages potentially reaching into the trillions of dollars. Power grids around the world could have been knocked offline for days or even weeks, and satellites would have been severely affected. The recovery from such an event could have taken years. This near miss serves as a stark reminder that while solar superstorms are rare, they are inevitable. It is only a matter of time before Earth experiences another Carrington-class event, and preparing for such an occurrence is critical. Given the potential for catastrophic damage from a solar superstorm, governments, space agencies, and industries around the world are taking steps to prepare for the next major event. Improving space weather forecasting is a top priority for mitigating the effects of solar storms. Instruments like NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter are providing unprecedented data on the Sun's activity, helping scientists better understand how solar storms form and how to predict their arrival. Power companies are working to harden their infrastructure against geomagnetic storms. Some utilities have installed geomagnetic monitors to detect fluctuations in the Earth's magnetic field, allowing operators to take protective measures, such as reducing the load on transformers or temporarily shutting down parts of the grid during a storm. Satellites are being designed with more robust shielding and fail-safes to protect them from the effects of solar radiation. Additionally, space weather monitoring systems on satellites help operators detect and respond to space weather events in real time. International collaboration on space weather forecasting and response is essential for protecting global infrastructure. Agencies like the National Oceanic and Atmospheric Administration, NOAA, and the European Space Agency, ESA, work together to share data and develop strategies for mitigating the effects of solar storms. While we cannot prevent solar storms, we can prepare for them. Understanding the history of solar superstorms and the damage they have caused provides valuable lessons for the future. The sun is a source of life and energy, but it also holds the potential for great disruption. By studying the sun's behavior and improving our space weather resilience, we can minimize the impact of future solar storms on our technology and society. The history of solar superstorms serves as a reminder of the sun's immense power, but the story of solar storms does not end here. As our exploration of the cosmos continues, we must consider the long-term effects of solar activity on the future of humanity, both on Earth and in space. The long-term effects of solar activity on humanity's future. As we look to the future, the sun's influence on our planet and our solar system will continue to shape humanity's destiny. Solar storms, the solar wind, and the sun's magnetic field all play a role in the space environment, affecting everything from our technology on Earth to the viability of long-term space exploration and colonization. While we have made significant strides in understanding the sun, the challenges posed by its volatile nature are only just beginning to unfold as we step further into the cosmos. In this chapter, we will explore the long-term effects of solar activity on humanity's future, from the implications for climate change and agriculture to the critical considerations for future space colonies and interplanetary travel. Solar storms are not just an immediate threat to our current technology. They are an ever-present factor that we must account for as we plan for the next century of space exploration. The sun is the primary driver of Earth's climate, providing the energy necessary for life to thrive. While solar activity is not the sole factor in climate change, fluctuations in solar energy output can influence Earth's weather and climate patterns over long periods. This raises important questions about how solar cycles could impact future climate trends and how humanity might need to adapt. Throughout history, fluctuations in solar activity have been linked to changes in Earth's climate. For example, the Maunder Minimum, a period of unusually low sunspot activity between 1645 and 1715, coincided with the Little Ice Age, a period of cooling that affected the Northern Hemisphere. While the relationship between solar activity and Earth's climate is complex, changes in solar irradiance, the amount of solar energy Earth receives, can contribute to natural climate variability. Today, we are entering what some scientists believe could be a period of reduced solar activity, potentially a new solar minimum. This could lead to a slight cooling effect on Earth's climate, though it is unlikely to offset the warming caused by human-driven climate change. The interplay between solar activity and anthropogenic factors such as greenhouse gas emissions is an area of ongoing research. Solar activity can also have a direct impact on agriculture, particularly in regions that rely on predictable seasonal weather patterns. Changes in solar radiation levels can influence crop yields, growing seasons, and water availability. During periods of intense solar activity, such as solar maximum, increased UV radiation can affect plant growth and photosynthesis. As global populations continue to rise, understanding the relationship between solar cycles and agriculture will be critical for ensuring food security. Farmers may need to adapt to shifting climate patterns caused by fluctuations in solar energy, using new techniques to optimize crop production in a changing environment. Governments and climate researchers are beginning to account for long-term variations in solar activity as part of broader climate models. While human activities remain the dominant driver of current climate change, future policies and adaptation strategies must consider the potential effects of solar cycles. For example, infrastructure, energy production, and water management systems may need to be designed with greater flexibility to account for the variability introduced by solar influences. One of the most exciting prospects for humanity's future is the potential for space colonization, whether on the Moon, Mars, or beyond. However, solar activity represents a significant challenge for long-term human habitation in space. Without Earth's protective magnetosphere and atmosphere, astronauts and colonists will be exposed to far higher levels of solar radiation, particularly during periods of heightened solar activity. Solar storms present a constant threat to astronauts and future space settlers. The lack of a thick atmosphere on the Moon or Mars means that solar energetic particles, SEPs, and cosmic rays can directly reach the surface. During a solar storm, these high-energy particles can penetrate spacecraft or habitat walls, leading to dangerous levels of radiation exposure. To mitigate this, future lunar or Martian colonies will need to incorporate radiation shielding into their design. This could include building habitats underground or using local resources such as lunar or Martian regolith to create thick protective barriers. Developing radiation-resistant materials and technologies will be essential for ensuring the safety of colonists during long-term missions, particularly in the event of a powerful solar storm. As humanity pushes deeper into space, solar energy will likely be a primary source of power for space colonies and spacecraft. Solar panels provide a reliable and renewable energy source, particularly in the inner solar system, where sunlight is abundant. However, solar storms can temporarily disrupt power generation by damaging solar panels or reducing their efficiency due to increased radiation levels. Spacecraft and colonies will need to be equipped with backup power systems to maintain energy during solar storms. These could include energy storage solutions like fuel cells or batteries, or alternative energy sources such as nuclear power for deep space missions where solar energy becomes less effective. Traveling between planets presents even greater challenges when it comes to solar activity. During long-duration missions, such as a crewed journey to Mars, astronauts will be exposed to solar radiation for extended periods. Without the protection of Earth's magnetosphere, they will be at greater risk from solar energetic particles, SEPs, and galactic cosmic rays. Spacecraft designed for interplanetary travel will need to be equipped with advanced radiation shielding and onboard storm shelters where astronauts can take refuge during a solar storm. In addition, space agencies will need to continue improving their ability to forecast solar storms, giving mission planners the ability to adjust trajectories or delay certain activities during periods of high solar activity. As we become increasingly reliant on technology, the potential impact of a major solar superstorm on Earth's infrastructure becomes more concerning. Satellites, power grids, communication systems, and transportation networks are all vulnerable to the effects of space weather, and a Carrington-class event in the modern era could have far-reaching consequences. Satellites play a critical role in modern society, enabling everything from GPS navigation to telecommunications, weather forecasting, and scientific research. However, these satellites are particularly vulnerable to the effects of solar storms. High-energy particles from solar flares or coronal mass ejections, CMEs, can damage satellite electronics, degrade solar panels, and interfere with data transmission. Future satellites will need to be built with more robust radiation shielding to withstand the effects of solar storms. Additionally, satellite operators may need to implement mitigation strategies, such as temporarily shutting down non-essential systems during a solar storm or adjusting satellite orbits to avoid areas of increased radiation. One of the most significant risks posed by a solar superstorm is the potential for widespread power grid failures. As we have seen with events like the Quebec blackout of 1989, geomagnetically induced currents, GICs, can overload transformers and cause blackouts that last for hours or even days. In a worst-case scenario, a Carrington-class event could lead to prolonged power outages across entire continents, disrupting essential services like water, healthcare, and communication. Governments and utility companies are investing in new technologies to harden the power grid against geomagnetic storms. This includes upgrading transformers to withstand GICs, installing monitoring systems to detect space weather threats, and developing contingency plans to reduce the load on the grid during periods of high solar activity. Ensuring the resilience of the power grid will be essential for maintaining stability in a world increasingly reliant on electricity. The threat posed by solar storms is not confined to individual countries or regions. It is a global challenge. As space weather forecasting improves, international collaboration will be essential for sharing data, coordinating responses, and protecting global infrastructure from the impacts of solar activity. Organizations like the International Space Weather Initiative, ISWI, and the World Meteorological Organization, WMO, are working to foster greater cooperation between nations in monitoring and responding to space weather events. By pooling resources and expertise, we can better prepare for the next major solar storm and minimize its impact on society. Understanding the sun and predicting its activity will be key to mitigating the risks posed by solar storms in the future. Ongoing and upcoming solar missions are providing unprecedented insight into the behavior of the sun and helping scientists develop more accurate models of solar activity. NASA's Parker Solar Probe, launched in 2018, is flying closer to the sun than any spacecraft before it, gathering data on the sun's corona, solar wind, and magnetic fields. The European Space Agency's Solar Orbiter mission is complementing this research by observing the sun's poles, regions that are difficult to study from Earth. These missions are shedding light on some of the biggest mysteries of solar physics, including the processes that drive solar flares and CMEs. The data they collect will help scientists improve space weather forecasting, giving us more time to prepare for solar storms and protect our infrastructure. Heliophysics, the study of the sun and its effects on the solar system, is a rapidly growing field. Researchers are developing increasingly sophisticated computer models to simulate the sun's magnetic field and predict when and where solar storms will occur. These models rely on data from solar observatories, satellites, and spacecraft to track solar activity in real time. Advances in heliophysics are helping us understand not only how solar storms form, but also how they propagate through the solar system and interact with planetary magnetospheres. This knowledge is essential for protecting astronauts, satellites, and infrastructure from the effects of space weather. The future of solar research holds the key to humanity's ability to thrive in an era of space exploration and technological reliance. As we continue to learn more about the sun's behavior, we will be better equipped to manage its effects on our planet, our technology, and our ventures into deep space. Solar activity will remain a constant factor in our future, but with continued research and innovation, humanity can adapt to the challenges it presents. As we push the boundaries of exploration and technology, the sun's power will always be both a source of energy and a reminder of the fragility of our place in the cosmos. The sun's life cycle, the future of our star and its impact on Earth. The sun, like all stars, is not eternal. While it currently resides in a stable phase, shining steadily and powering life on Earth, its life cycle is a cosmic process that will eventually lead to dramatic changes both for the sun itself and for the solar system. Understanding the future of our sun and its eventual demise helps us appreciate both the scale of astronomical time and the inevitable transformation of our solar environment. In this chapter, we'll explore the life cycle of the sun, how it will evolve in the distant future, and what that means for Earth and humanity. Although these changes are billions of years away, the fate of our star is intimately linked to the future of the solar system as a whole. The sun is currently in the most stable and longest phase of its life cycle, known as the main sequence. This phase began approximately 4.5 billion years ago, when the sun first ignited nuclear fusion in its core, turning hydrogen into helium and releasing vast amounts of energy. This process powers the sun and will continue for roughly another 5 billion years. At the core of the sun, immense pressures and temperatures cause hydrogen atoms to collide and fuse into helium, a process that releases energy in the form of light and heat. This energy radiates outward, eventually reaching Earth and providing the energy necessary for life. During the main sequence, the sun is in a delicate balance between two forces: the inward pull of gravity, which tries to collapse the sun, and the outward pressure generated by nuclear fusion in the core. This balance keeps the sun stable, neither shrinking nor expanding dramatically. Over the course of its main sequence, the sun's energy output has gradually increased. When the sun first formed, it was only about 70% as bright as it is today. This gradual increase in solar luminosity is known as the solar luminosity problem, and it has implications for the long-term habitability of Earth. While the Sun remains stable during the main sequence, it will not last forever. The supply of hydrogen in the core will eventually run out, triggering a series of changes that will transform the Sun into a much different star. In approximately 5 billion years, the Sun will exhaust its core hydrogen fuel, and it will begin to enter the next phase of its life cycle, the red giant phase. This transformation will have profound consequences for the solar system, especially for the inner planets, including Earth. When the hydrogen in the core is depleted, the core will begin to collapse under its own gravity, causing temperatures and pressures to rise. At the same time, hydrogen fusion will continue in a shell surrounding the core, leading to an increase in energy output. This will cause the Sun's outer layers to expand dramatically. As the Sun's outer layers expand, it will grow to many times its current size, potentially engulfing the inner planets, including Mercury and Venus. Whether Earth is swallowed by the expanding Sun remains uncertain. Current models suggest it may be close to the edge of the Sun's outer envelope. Even if Earth remains outside the Sun's reach, the intense heat and radiation from the swollen red giant will render our planet uninhabitable, boiling away the oceans and stripping away the atmosphere. During the red giant phase, the Sun's luminosity will increase significantly and its surface temperature will drop, giving the Sun a reddish hue. This phase will last for around 1 billion years, during which time the Sun will lose much of its mass as its outer layers are blown away by powerful stellar winds. The red giant phase is a dramatic transformation for the Sun, and it will signal the end of the solar system as we know it. The inner planets will be scorched or consumed, and the outer planets may see their environments change as well, with their icy surfaces thawing due to the increased heat from the Sun. Once the Sun has burned through the hydrogen in its outer layers and begun fusing helium into heavier elements like carbon and oxygen, it will reach the end of its red giant phase. This will set the stage for the final chapter in the Sun's life: the formation of a planetary nebula and the emergence of a white dwarf. After shedding its outer layers during the red giant phase, the Sun will become unstable. The outer layers of gas will be ejected into space, creating a glowing shell of ionized gas known as a planetary nebula. These nebulae are often stunningly beautiful, with intricate shapes and colors created by the interaction of the Sun's stellar winds and the surrounding interstellar medium. The planetary nebula will expand over tens of thousands of years, eventually dispersing into space, leaving behind only the Sun's core. At the center of the planetary nebula, the remaining core of the Sun will become a white dwarf, a small, dense remnant composed mainly of carbon and oxygen. This white dwarf will no longer generate energy through fusion, but will instead glow faintly as it cools over billions of years. White dwarfs are incredibly dense. 1 teaspoon of white dwarf material would weigh tons on Earth. Over time, the white dwarf will continue to cool and fade, eventually becoming a cold, dark remnant known as a black dwarf. However, this process will take far longer than the current age of the universe, meaning that no black dwarfs have yet formed. As the Sun becomes a white dwarf, its gravitational influence on the solar system will diminish. The outer planets may drift farther away, and the remaining debris from the planetary nebula will spread out into the interstellar medium. By this time, any remnants of the solar system will be cold and dark, a far cry from the vibrant, life-sustaining system we know today. The Sun's evolution into a red giant and eventually a white dwarf will have profound consequences for the solar system. While these events are billions of years in the future, understanding their impact helps us appreciate the long-term dynamics of stellar evolution and planetary systems. Earth's future is tightly bound to the Sun's evolution. In about 1 billion years, well before the red giant phase begins, the increasing brightness of the Sun will make Earth's surface temperatures rise. This will likely cause the oceans to evaporate, creating a runaway greenhouse effect similar to what we see on Venus today. Long before the Sun becomes a red giant, Earth will become uninhabitable, forcing humanity to either adapt or find a new home elsewhere in the solar system or beyond. As the Sun evolves, the outer planets, Jupiter, Saturn, Uranus, and Neptune, may experience significant changes. During the red giant phase, the increased heat from the Sun could cause the icy moons of these planets to melt, potentially creating temporary oceans or atmospheres. However, this period will be short-lived, as the Sun's transition to a white dwarf will result in a sharp decrease in heat and energy. The intense solar winds and radiation during the red giant phase may strip away the icy surfaces of comets and asteroids, altering their orbits or even ejecting them from the solar system entirely. The asteroid belt between Mars and Jupiter may also be affected, with its objects either colliding with each other or being pushed into new orbits. While the timeline for the Sun's evolution spans billions of years, the fate of humanity is intricately tied to the long-term dynamics of our star. As the Sun gradually grows brighter, life on Earth will become increasingly difficult, forcing humanity to either find technological solutions or migrate to more hospitable environments, such as other planets or even other star systems. As the Sun's heat increases, the outer regions of the solar system may become more attractive for colonization. Moons like Europa, Ganymede, or Titan, currently cold and icy, could become more habitable as the Sun warms them. This could open up new frontiers for human exploration and settlement in the far future. The eventual transformation of the Sun into a red giant may prompt humanity to look beyond the solar system for a new home. Developing technologies for interstellar travel, such as generation ships, warp drives, or wormholes, could become a priority for ensuring the survival of the species as the Sun's life cycle progresses. In the near-term future, the Sun will continue to be an abundant source of energy for Earth and space-based civilizations. Projects like Dyson spheres, hypothetical megastructures designed to capture the entire energy output of a star, could provide limitless energy for future generations. By harnessing the power of the Sun, humanity could ensure a sustainable energy supply as we expand into the solar system and beyond. The Sun's life cycle reminds us that stars, planets, and even entire solar systems are temporary in the grand scheme of the universe. As we look toward the future, we must acknowledge that our time in the solar system is limited, and that the Sun's eventual demise will require humanity to adapt and evolve in ways we can only begin to imagine. Understanding the Sun's future helps us put our place in the cosmos into perspective. While the timeline for these events spans billions of years, the evolution of the Sun is a powerful reminder of the dynamic nature of the universe and the need for continued exploration, discovery, and innovation as we prepare for the distant future. As we contemplate the Sun's eventual transformation into a red giant and white dwarf, we also turn our attention to the larger cosmic forces at play. Solar storms, stellar evolution, and the death of stars are part of the ongoing story of the universe, one that we are only just beginning to understand. The role of solar activity in cosmic evolution. While we've spent much of this journey focusing on the Sun's influence on Earth and the solar system, it's important to recognize that solar activity and the life cycle of stars in general play a key role in shaping the broader cosmos. The Sun is just one of billions of stars in our galaxy, and the processes that govern its behavior are mirrored across the universe. From the creation of elements in stellar cores, to the violent supernova explosions that seed galaxies with heavy elements, solar and stellar activity are fundamental to the cosmic cycle of birth, death, and rebirth. In this chapter, we will explore how solar activity fits into the larger picture of cosmic evolution, the creation of elements, and the role of stars in building the structure of galaxies, planets, and ultimately, life. Stars like the Sun are often referred to as the engines of the universe because they are responsible for creating most of the elements that make up everything around us. This process, known as stellar nucleosynthesis, takes place in the cores of stars and is responsible for producing elements heavier than hydrogen. Shortly after the Big Bang, the universe consisted primarily of hydrogen and helium, with trace amounts of lithium. These were the only elements created in the early universe through a process called Big Bang nucleosynthesis. It wasn't until stars formed that the heavier elements began to emerge. During a star's lifetime, the immense pressure and heat in its core cause hydrogen atoms to fuse together to form helium. This process releases vast amounts of energy, which powers the star and radiates outward into space. As the star evolves, it begins to fuse heavier elements. For stars like the Sun, this process produces elements such as carbon, nitrogen, and oxygen, key building blocks for life. More massive stars are capable of fusing elements beyond helium, producing neon, magnesium, silicon, and eventually iron in their cores. This sequence of element production is known as the stellar fusion chain, and it represents the creation of most of the elements found in the universe today. The creation of elements heavier than iron requires even more extreme conditions than those found in the core of a star. These elements, such as gold, uranium, and platinum, are formed during the explosive deaths of massive stars in supernovae or in neutron star collisions. These cataclysmic events release enormous amounts of energy, creating the conditions necessary for the formation of the heaviest elements. In this way, the Sun and stars like it serve as forges, creating the elements that make up planets, moons, and life itself. Every atom in our bodies, from the carbon in our cells to the calcium in our bones, was formed in the heart of a star billions of years ago. Our Sun exists within the Milky Way galaxy, a vast collection of stars, planets, and cosmic material bound together by gravity. Within the galaxy, stars, gas, and dust move in intricate patterns, shaped by the gravitational pull of massive structures such as black holes and dark matter. The life cycle of stars, including the Sun, plays a significant role in maintaining the dynamic equilibrium of galaxies. New stars form from the collapse of giant clouds of gas and dust known as molecular clouds. As these clouds collapse under gravity, they begin to spin, forming a rotating disk of material that will eventually give birth to a new star and its planetary system. The solar wind, an outflow of charged particles from the Sun's corona, mirrors similar processes in other stars. These winds blow away residual gas and dust in a young star system, helping to clear the path for the formation of planets. Without solar and stellar winds, planetary systems would remain surrounded by dense clouds of gas, making planet formation difficult. While stars like the Sun are important for creating elements, the most massive stars, which end their lives in supernova explosions, are the key drivers of galactic evolution. When a supernova occurs, it releases an immense amount of energy, sending shock waves through space that can trigger the collapse of nearby molecular clouds, leading to the birth of new stars. Supernovae also play a crucial role in distributing heavy elements throughout the galaxy. The elements created in the core of the star, as well as those formed during the explosion itself, are ejected into space, enriching the interstellar medium with the raw materials needed for future stars and planets. This constant cycle of star birth, death, and rebirth drives the evolution of galaxies, helping to maintain the balance between the creation of new stars and the dispersion of old ones. While we've focused on the solar wind and solar energetic particles, SEPs, emitted by our Sun, there are also high-energy particles that originate from beyond the solar system. These particles, known as cosmic rays, are some of the most energetic particles in the universe and play a role in both the evolution of galaxies and the formation of stars and planets. Cosmic rays are generated by a variety of high-energy astrophysical events, including supernova, gamma-ray bursts, and black hole activity. These particles, primarily protons, are accelerated to near the speed of light by the shock waves generated by these events. Once they are accelerated, they travel through space, occasionally interacting with planets, stars, and interstellar matter. While Earth's magnetosphere protects us from most cosmic rays, some still penetrate the atmosphere, where they can interact with atmospheric particles and create secondary cosmic rays. These interactions are part of the background radiation that astronauts, aircraft pilots, and even people at high altitudes experience. In deep space, away from the protection of Earth's magnetic field, cosmic rays pose a significant radiation hazard to both astronauts and spacecraft. Cosmic rays also play a role in the formation of stars by influencing the temperature and ionization of molecular clouds. High-energy cosmic rays can ionize gas in these clouds, which in turn affects the rate at which stars form. Cosmic rays can either inhibit or enhance star formation, depending on the conditions within the cloud. This connection between cosmic rays and star formation highlights the interconnectedness of various cosmic processes. The life cycle of stars, the distribution of elements, and the formation of new stars are all influenced by both local stellar activity and distant cosmic events. As we continue to study the Sun and other stars, our understanding of stellar evolution and its impact on the universe will deepen. Future solar missions and astronomical research will help us unravel the remaining mysteries of the Sun's behavior, including its magnetic field, its long-term evolution, and the forces driving solar activity. Missions like NASA's Parker Solar Probe and the European Space Agency's Solar Orbiter are already providing new insights into the Sun's outer layers and magnetic field. However, future missions will aim to explore even deeper into the Sun's interior and provide more precise measurements of its activity. This data will be critical for improving our understanding of solar storms and their impact on space weather. Beyond our own Sun, astronomers are using tools like the Gaia spacecraft and large ground-based telescopes to map the positions, motions, and properties of billions of stars in our galaxy. This data is helping scientists develop more accurate models of stellar evolution and understand how stars like the Sun evolve over time. By studying stars at different stages of their life cycles, astronomers can gain a better understanding of how solar activity fits into the broader picture of cosmic evolution. The data gathered from these surveys will also help identify potentially habitable exoplanets and improve our understanding of planetary system formation. As we learn more about the role of solar activity in the formation of planets and the development of life, the search for life beyond Earth will become increasingly informed by our understanding of stars. Planets orbiting stars similar to the Sun, often referred to as solar analogs, are prime candidates for the search for extraterrestrial life. However, the habitability of these planets will depend not only on their distance from the star, but also on the star's activity levels. Active stars with frequent solar flares and CMEs may pose a significant challenge for life to develop and persist on nearby planets, particularly if those planets lack protective magnetic fields. As we continue to explore exoplanets and other star systems, solar activity will remain a key factor in determining the potential for life. At the largest scale, stars, including our Sun, are the fundamental building blocks of the universe. Through their life cycles, they create and distribute the elements necessary for the formation of planets, moons, and living organisms. They power galaxies, drive cosmic evolution, and, in many ways, are responsible for the structure of the universe itself. Stars and the stellar winds they produce shape the structure of galaxies by dispersing gas and dust. Massive stars, in particular, play a critical role in clearing out regions of space and driving the formation of new stars and planetary systems. On the grandest scales, the universe is structured like a web of filaments, with galaxies and clusters of galaxies connected by vast strands of dark matter and intergalactic gas. Stars are the luminous markers of this cosmic web, lighting up the vast darkness of space and serving as beacons for future exploration. The Sun, as a relatively small star in this cosmic web, may seem insignificant compared to the larger structures of the universe. However, its activity and life cycle are part of the same processes that shape the cosmos on every scale. As we continue to study the Sun and other stars, we deepen our understanding of the universe's past, present, and future. As we reflect on the Sun's role in cosmic evolution, we are reminded of our place in the universe. The life and activity of stars are intimately connected to the existence of planets, life, and the very fabric of space-time. From the creation of elements to the formation of new stars and galaxies, the Sun's story is part of the larger narrative of the cosmos.